Hello everyone, I am Pragya Srivastava. I am here to record a lecture on ion implantation, and the subject is VLSI technology and the course code is KEC 053. In my previous lecture we have studied what is electron beam lithography. In this lecture we are going to study the next step of electron beam lithography, that is ion implantation. So in electron beam lithography we were successfully able to remove the excessive silicon dioxide or whichever layer which we wanted to remove. Then after the removal of successful removal of let's say silicon dioxide from a particular site, now we want to add some dopant or we want to add some semiconductor, let's say N plus or N type, or we want to create some well at a specific site. So to achieve this we have process, let's say diffusion or ion implantation. So diffusion and ion implantation both are the methods which will solve the same purpose of adding dopant, desired dopant at desired sites. When we talk about both the methods, we have some comparison in these two, like diffusion and ion implantation. We will study about everything in this lecture. So when we are actually thinking of impurity doping, there are two methods of introducing impurities to silicon to control the majority carrier type and the resistivity of layers. These two methods are diffusion and ion implantation. So dopant atoms move from the substrate into silicon by thermal means, that is via substitutional or interstitial diffusion mechanism. Now what is the substitutional and interstitial diffusion mechanism? Let's say we have a parent lattice, and then in this parent lattice I want to add some dopant. So let's say this is the foreign dopant molecule which I want to add. So when I am adding it here and the previous parent molecule moves out of the geometry and the blue or the dopant acquires its space and the red or the parent is thrown out of the lattice. This is my lattice. So it is nothing but an act of substitution. Now there is another act where we can do it in a method called interstitial. So what we are actually doing in interstitial, what is happening, the foreign molecule will come and take place and it will not remove the parent atom. So this is called interstitial diffusion. So we have substitutional or interstitial diffusion. So whether substitutional or interstitial, both is a process which is thermal enabled. Now next is ion implantation. So ion implantation is altogether a new step where dopant atoms are forcefully added to silicon lattice in the form of energetic ion beam injection. Let's say we have an ion source. Let's say we have an ion source here. I am drawing a rough diagram, and this ion source will have a trunk and it will direct the nozzle on directly to the wafer. Let's say we have a wafer. So this was a wafer like this. We have always seen it like this. I have rotated it, and then this ion implanter will add the ions only at the particular site where we need it. What is the need of doping? So first of all, formation of PN junction and fabrication of device during wafer fabrication. We can alter the type and level of conductivity. Sometimes we can increase the level of conductivity and sometimes we can decrease the level of conductivity. We can change the type of semiconductor material, and it forms the different region like base, emitter, or source, drain and gate. So with the help of doping we can achieve anything and everything. So as well as drains and sources in MOSFETs. Also with the help of doping we also achieve polysilicon layers. So this all is the purpose of doping. Now here we can see the difference between doping and an implantation. So we see that high temperature, and for this we require a mask which is silicon dioxide mask, and it is having isotropic dopant profile. We can see that the atoms which we are adding, the profile which we are adding will be isotropic, and the diffusion, the well will be isotropic in nature. Cannot independently control the dopant concentration and junction depth. So it is not a precise process. Here the control of junction depth and dopant concentration is not possible. Now here in ion implantation, it is a low temperature, and we are having a PR mask which is photoresist mask. The process is anisotropic dopant profile. We can see that the diffusion profile is more in vertical direction and less in horizontal. So the process is not isotropic, it is anisotropic, and it can independently control. Yes, here we have a precise control about dopant concentration and the junction depth. So accordingly we have a better control on the dopant concentration and the junction depth. Here in this diagram we have profiles where we are trying to add metals, not the metals, dopant atoms. So doping profile, we can see that here gas of dopant atoms, and we can see that the overall envelope of the well has become like this, and here we have high velocity dopant ions. So it is like this. So we can see the difference between the two processes, and we can see the presence of the method to add dopants. We can understand there is only a difference between a procedure in which we are adding the dopants. So it is a contamination free process. The dominant, accurate and low temperature doping control method, and it has an excellent control of dose with large range of like 10 raised to the power 12 to 10 raised to the power 18 dopants per centimeter square, and it is a non-equilibrium process. Good control of implant depth, that is 100 angstrom to 10 micrometer, with energy of few electron volts to few kilo electron volts to few mega electron volts. So repairing or crystal damage and dopant activation requires annealing, so which can cause dopant diffusion and loss of diffusion depth control. So this is a disadvantage. We have to go through a process of annealing, which sometimes alters the junction depth and depth control. So there is a wide choice of making materials. We can fill the implanter with any material. So an implantation is basically a semiconductor conduction property can be changed by introducing small quantity of dopant atoms. So there is a need of a method which will introduce the dopant that is controllable, reproducible and free from undesirable side effects. So in diffusion, always the surface concentration is going to be highest, and after that it is going to follow either the complementary error function or the Gaussian profile. The Gaussian profile is nothing but this one. If we want to bring down the surface concentration, necessarily we have to go deeper. So these two factors, the surface concentration and the depth, they are interrelated in case of diffusion. So coming on to doped regions, we have here, we can see that we are showing two diagrams for diffusion and ion implantation. On the left hand side, we have a profile of diffusion based well, and then we have a profile of ion implantation based well. So here we can see that this junction depth, to be more accurate, when we are doping it with the help of diffusion, it is sometimes like this. So when it is like this, the junction depth, which should be only this, is not met here, but it is met here. So this junction depth is a very important parameter which is taken care of only in ion implantation and not in diffusion. So if you ask anyone to take a choice between diffusion and ion implantation for better junction depth, the answer will be ion implantation. During ion implantation, dopants are vaporized, accelerated and directed at silicon substrate. So there will be a nozzle and there will be ions which will hit the cavity of the wafer. They enter the crystal lattice, collide with silicon atoms and gradually lose energy, finally coming to rest, and at some depth within the lattice they will acquire a space. The average depth can be controlled by adjusting the acceleration energy. The dopant dose can be controlled by monitoring the ion current during the implantation, and the dopant initials stated with high energy electron beam, and then once they have penetrated the semiconductor surface, they begin to lose their energy, and at the end of the process, the process is actually losing of energy can either be achieved by colliding with the lattice atom or with the help of elastic collision. So once they lose energy, they will try to settle down. Now we have to see what is the stopping mechanism. When the ions go for nuclear stopping, when the energetic ion loses energy by colliding with the lattice atom, so that is nuclear stopping, losing energy to the lattice and in the process creating point defects. So this is vacancies and interstitial, this is nuclear stopping. When we talk about electronic stopping, the energetic ions supplies their energy to bond of electrons. In this process, the bond electrons become the free electron and they gain energy, and they call it electronic stopping. So here they don't create point effects, and here they don't create vacancies and interstitials. So one is nuclear stopping, another is electronic stopping. Here we are trying to show the concept. Let's say we are having a ion source, and we have tried to list some examples of the ion source. So we are putting the ion source in the ion implanter. Let's say this is the ion implanter. So ion implanter is also having an accelerator column, which will do nothing but it will speed up the electrons which are entering or which are leaving from the surface of ion nozzle, and then there will be wafers, and at the specific point there will be process of ion implantation will take place. So this is a general setup. Now we can see that how the overall process of electron beam ion implanter ion implantation looks like, not the electron beam one. So this is a complete setup which we have to understand, that how it helps us in achieving diffusion or adding the required dopant at particular place. Now to start with, we have an ion source here. This ion source will supply ions. Now once these ions are created, they are having an analyzing magnet which will route them for 90 degrees. They are created and then routed. So this is nothing but a 90-degree shift. So when they are 90-degree shifted, they are then passed into a tube where they are accelerated. This acceleration will help them in getting a speed. So the ions which are moving from here, we can also see this is the acceleration tube here, and the ions are getting accelerated. But after getting accelerated, they try to diverge. They get a tendency, and after that tendency, they try to diverge. When this diversion is taking place, we are trying to limit the diversion with the help of deflection plates. So once we are having certain deflection plates, so this deflection plates, like with this passage, there will be Y deflection plates. One Y deflection plate is seen here. Another deflection plate will be at the back side of it, and they have not drawn it. So there will be Y deflection plates which will allow or direct the ions which were deflecting in Y plane. So now they are deflecting in Y plane, and we are putting the Y deflection plates, so all the deflection will stop and they will focus straight. Now after crossing to the Y deflection plates, now they are not deflecting in Y direction, they are going straight. So they are going straight. What if they start deflection in X plane? So we have to put some X deflection plate also, so that they go straight. So now we have converged it in this plane, and then we have converged in this plane. So there will be a point target now. So getting a point target, here is the wafer, and to draw it more accurately, I am drawing it. So at this point we will get the ion beam. So there is neutral and beam path gated, and the wafer is placed at the end of the chamber. The wafer may be clamped and held with centrifugal force. A batch of wafers are implanted at the same time. We also see that here in ion implantation, it is a big and specific setup. So in this setup, what we are actually trying to do is to add dopant at a particular place with a particular junction depth. So it is altogether a very dedicated setup which is only used to add dopants. So when we compare to diffusion profile, of course the quality is better, and the depth control is fine, but at the same point it is a costly setup which requires dedicated space, and also it requires due time to allocate the ions and to make the process complete. Comparison of diffusion and ion implantation. As I have said, ion implantation is a costlier method. So diffusion is of course a cheaper, and more simplistic method, but can only be formed from the surface of wafers. Dopants also diffuse unevenly and interact with each other, altering the diffusion rate. Now, an implantation is, as compared to expensive and complex process. It does not require high temperature, and it also allows for greater control of dopant concentration and profile. It is an anisotropic process. Now, diffusion was an isotropic process, therefore does not spread and dopant implant as much as diffusion. So, we have seen in the previous slides also, an implantation is not at all spreading and it is spreading everywhere. So, this is what we were talking about. This aids in the manufacture of self-aligned structure, which greatly improves the performance of MOS transistors. In this diagram, we are going to study how when an ion is entering into the lattice, the movement of ion in the wafer. See, we can see that sometimes this ion is entering, and we can see that it is a process where number of collisions which are taking place are more, and the required dopant atom is not able to reach at the rear end of the lattice. Sometimes it happens that we are adding or we are projecting at a particular angle so that channeling occurs, means less and less collision is occurring, and the dopant is least, is the collision of dopant is very less, and we reach almost to the mid of the lattice. So, this is called channeling, and there is also a process where backscattering is taking place. Backscattering means there was a molecule here, it hit it, after hitting this it gets back. So, this is the worst case and this is the best case, channeling. So, to have a comparison between nuclear stopping and electronic stopping. So, nuclear stopping caused by collision with nuclei of the lattice atoms, and on the other hand, elastic collision is happening with the electrons of the lattice atoms. So, scattering significantly and causes the crystal damage, whereas in electronic stopping the energy is transferred in a very small magnitude. So, nuclear stopping is elastic collision, whereas electronic stopping is a negligible crystal structure damage. So, we will also study more on channeling. What is happening in channeling? If the incident angle is right, ion can travel long distance without collision with lattice. It causes uncontrollable dopant profile. We can see that we are adding a dopant in this direction. It will hit, first it will hit this molecule, then this molecule, then this molecule, then this molecule, then this molecule. So, it has had first collision, second collision, third collision, fourth collision, and then fifth collision. So, the chances of entering into the at the higher dimension and higher depth is very, very poor. So, let us call about the another angle where we are trying to add from this point of line. Here you say it goes straight. If you are adding here also it goes straight. So, we have very, very few collision and the chances of entering into the lattice is very, very good. So, here we have to study the effect of channeling. Let us say at some point of lattice we are having collision, then we are having channeling. At this point we have somehow achieved channeling, and then again some collision is there. So, we can see the three when we talk about dopant concentration and the distance covered. So, here you have covered less distance, here you have covered more distance, then here also we have covered as far as the distance is spanning, the dopant concentration is, due to collision, it is not helping any way. Now, the other method in which ion beam is lacking is, sometimes what is happening, there is a method where shadowing effect takes place. In this shadowing, we have the electron beam is not able to penetrate a particular section. We can see the electron beam was not able to penetrate this given blue section because it was shadowed from the polysilicon. So this is called shadowing effect. In case of electron beam, this is a flaw, whereas in case of diffusion, the required molecule, if let's say we are going to diffuse, the required molecule will diffuse like this. So this cloud, this shady area and this shadowing effect will never take place in diffusion. And after we have gone through a process of annealing, of course, this added doped region will extend up to a bit, but it will not solve the purpose to next an extent. Now, in this crystal, we are in this slide, I am trying to show the lattice damage with one ion. What is actually happening? Let's say we are adding a light ion. So when we are adding the light ion, it is entering to the lattice and it is, hitting multiple other ions which are already present. So this is the journey of light ion. Let's say we talk about heavy ion. Having heavy, we mean to say molecular weight and the dimensions. So it is not able to reach the device dimension as far as light ion is concerned. So crystal damage is more in heavy ion and less in light ion. Now, with the help of ion implantation, we are actually leading to before implant and after implantation process. There is a lattice mismatch, or not only mismatch, after the collision there happens to be a situation where the overall lattice gets disturbed. So when this lattice gets disturbed, what we are actually going to do? We are going to perform annealing. Annealing is a correction process in which thermal energy from higher temperature will help in settling down. Now what I will be doing is, I will be trying to show you, here it is a process. We can see that we have added certain dopants here, and with the help of these dopants, the overall lattice is disturbed. I will try to scroll more slides in a fast method, and we can see that how this bottom settled layer will move, and we can see slide 1, less settled, it is more settled, even more settled, even more settled, even more settled, ever more settled, and settling process goes on, and the complete lattice is settled. So this is thermal annealing. Going back, we can see this is how annealing started. Last layer settled, second last settled, third last settled, fourth last settled, fifth last settled, and then the top third layer, top second layer, and the topmost layer is settled. So it is a process where thermal annealing is helping in the device geometry. That was all from my side, and this was a lecture, and we have studied how lithography and ion implantation have been a helpful process in IC fabrication. Thank you.